But that, like for, just a circle, it kind of works in 2D, but like for even circles in like 10,000 dimensions, that's not going to work. So neural networks, basically, they solve this in a very clever way by saying, okay, neural networks. So we had like a linear layer here. So this was my input, matrix multiplication, and then my score is my output. And that's what the formula was. So now let's say that what I want to do is just compose the two. I want to compose this. So I want to take the output that I had here and just use that as an input to another linear classifier before I get like the thing that I interpret as my score now. So basically, I'm just composing two linear models with each other. So now I don't want this to be equivalent to a single linear model, so I need to have a nonlinear function here. So I've called it G. I'm confused. This is, what letter is that? G. This is G? Okay. My brain is French right now because I'm teaching in French, and so this is extremely confusing. I'm sorry. Okay, neural networks fine, letters no, not fine with my brain. Okay, okay. So I'm just like composing the two functions, right? But then if like this was identity, for example, if this was a linear function, I could just rewrite like W1 and W2 as a single matrix, and it would be just back to a single linear model. So if I don't want this to be equivalent to a linear model, then I have to have some nonlinear function here. So I'm going to be composing functions and separating them by nonlinear functions. Okay, so what's going to happen now? Oh yeah, so that's called like a neural network. So why is it called like, what is the neuron in neural network? So so a neuron, basically the way it works is it has a bunch of like dendrites that have some conductivity and they receive signal. And then that signal is combined in the nucleus. And then if it passes some like nonlinear threshold, it gets activated and it fires through the axon. And then the signal gets passed through. So the analogy is that like every one of the like H values that I have here in that middle like vector, it can be thought of as a computational unit the same way that a neuron can be thought of as a computational unit. So basically I have like the input that comes from my x's and they get multiplied by some conductivity like the weight W, and they get combined inside the computational unit. And then I have this like nonlinear activation that activates, it tells me how much signal gets put through to the next layer, basically. So that's kind of the analogy. So, and because of that, because like a network, like a neuron in like a brain gets activated if there's like past a certain threshold, that's like that nonlinear function is called the activation function, because that's by analogy with a network, a neuron, a physical, like biological neuron that gets like activated past a certain threshold. Okay, so now I can represent basically my linear model instead of having like my vector input, my matrix, and my vector output as a bunch of neurons that are connected with the neurons of the next layer like that. So here I have 10 classes for like CFAR, so it's going to be 10 neurons, and they're all connected by a bunch of weights. So every line is a weight in that matrix multiplication here. Okay, and then if I have another layer, then I can just like keep on going like this and have another set of weights here and keep on going like that. So it's called a neural network because it's a network of neurons in this representation. Make sense? Okay, so that's kind of where the name comes from, is by analogy with biological neurons. Okay, and then when I put an image or a vector of input through the network and I calculate like, I just follow through like I do the matrix multiplication. I get the here after the neurons after the activation, and then I pass them through the second series of weights, and then I get my final output to get like the output of the whole thing. That's called the forward pass because it goes forward. Okay. So then the output is going to be basically the composition of like the two weights, the two layers of weights with each other. Okay. So now we have something. So we had something that was very limited when we had just like a one-layer network, just a linear model. We couldn't model many things. Now that we have even just 2 layers, we have something very interesting that happens. So there's a theorem that's called the universal approximation theorem. And what it tells us is that just for like, we can basically, with a network like that, if we have enough neurons in the layer 1, like the hidden layer, the hidden neurons that we don't see, we can approximate any arbitrary function to an arbitrary accuracy. Well, as long as it's kind of a reasonable function. So the functions that we would care about, we can approximate any function to arbitrary accuracy with just a 2-layer neural network. And so now we can do a lot more things if we have enough like neurons in layer 1. Okay, so before we had this as our template, but so that's what comes out of my first layer of the neural network. Now I put that through some activation function, and I take linear combinations of those through this second layer of the network. And so just for like the horse, now I'm going to start having a lot more possible things I can be looking for that are a lot more complex. And like specifically, I'm going to have like horses that are facing, this is right, and horses that are facing left. And so now I have like templates that I'm finally looking for where I can separate different like islands in like different like clumps, different clusters in my pixel space. So basically, I get like a lot more templates now for things that I'm looking for. And yeah, so it allows to store a lot more templates for like every given class, so it's a lot more impressive, and then we can find a lot more things. Okay, so now the question is, how are we going to optimize all those weights? Because before we could just find like, we could find gradients like exactly. And so we're going to do just exactly the same thing. We're going to define a loss function that tells us how well we're doing. It's going to be the same loss function. And then we're going to try to optimize it using gradient descent exactly the same way that we did before. And so what that means is that we need to find the gradients of the loss with respect to those weights. And so this is where something called backpropagation comes in. So before, like I said, we needed to have the exact gradients, not finite differential gradients. And so we want to do the same thing here. But like all the functions that I have, they're the same functions that I had before. I've just been composing, right? So I can write, again, the gradient analytically. And you probably remember from calculus that there's something called the chain rule that allows you to take derivatives of composed functions. And so the nonlinear function, like the activation function, is also going to be a differentiable function. So basically, what backpropagation is just a fancy word for taking the chain rule to get exact gradient at every layer of the network. So if you're happy with the chain rule, we can just move on very quickly, because this is literally just taking the chain rule. And so you would think, okay, this is going to be really tedious. Like if I have 150 layers in my neural network, I'm going to have like 150 times I'm going to have to take the gradient. But there's some people at Google and at Facebook that have spent a lot of time writing all those functions under the hood, so you never actually have to write it down. So the gradients are already there. You don't need to. If you use like a machine learning library, you don't need to code your gradients yourself. Backprop is already coded in there. So it's under the hood, and you never need to actually do it. It's just there. OK, so I'm just going to skip that very quickly. This is just how to calculate gradients with the chain rule. And then, at one neuron, gradient comes back out, and then we can just keep on going with the chain rule. OK, so now we have our gradients, so we need to find the learning rate to optimize with like downhill optimization. And we're done. So we have a bunch of different optimizers. So I showed like downhill gradient descent, but like there's a bunch of fancier optimizers that have momentum that allow to converge better. And so whenever you're doing machine learning, you should just use Adam optimizer, because it's awesome. So that's the optimizer that you should always be using. Don't use anything else. OK, activation functions. So I said that between like every one of your linear like layers, you need to have an activation function that's nonlinear. Otherwise, it would just collapse to like being just a single linear layer. So these are a bunch of different choices that we have for different activation functions that have been used historically. In practice, these are the only ones you want to use. So by default, you want to use ReLU, because it's great. And then if it doesn't work really well, then you might want to explore leaky ReLU or like exponential ReLU. And that's all you need to know. OK. All right, so summary. So we have some data set, X and Y's, and we want to use it to find what are the weights at the different like layers of my neural network. And so what I do is I write a cost function that represents what I want my network to do. That like allows me to map the X to the Y. And then I calculate the gradients of the weights with respect to that loss function with backprop for a mini batch. I give those gradients to a downhill optimizer like Adam optimizer, and then I update the weights, and then I keep on going like that. I go back to step 2 and keep on going until the process converges. And then I'm done. Clear? Yeah? Yes. And make people run.
So my question actually goes back to the slide where you had the overview of the 2-layer system. You have the input parameters X and the output S, and then H in the middle. Are there
Yeah,
any
maybe I
limits
changed
on the
letters.
dimensionality of H? Does it need to match
Yeah,
either
so basically the universal approximation, no, it could be anything you want, as long as like, you pipe it up together. Like, a matrix can have a number of rows and a number of columns. As long as the number of columns you have match how many neurons you have like in your hidden layer, and it matches what's coming out after, then you're good.
So the dimensionality of the 2 weight matrices on either side are determined by H, but H can be whatever you want, however
Yeah,
many
and
neurons.
typically the way you code this up, actually, when you write down a neural network, is you tell it how many neurons you want to have in the hidden layer, and it's going to figure out how many weights it needs to have by itself.
Cool.
So you never need to actually code the matrix multiplication, because that's really optimized in like, so the backend is like C++. I think it's in Python, so like the backend is C++, so it's super efficient. And so yeah, so it's like it's all vectorized and it goes super fast and it's great. So you just tell it how many neurons you want to have in your hidden layers, and it's going to figure out what it needs to do. Yes, and so the universal approximation theorem, it doesn't tell you how many neurons you need to have in your hidden layer. So the hidden layer is the one that you don't get to see, like it's the layer 1. So it doesn't tell you how many you need to have there. So it could be that for a very, very, very complicated function, you need to have like a lot of weights. And so in practice, like that's not how we end up coding neural networks. Is there another question?
What exactly makes Atom like the best optimizer?
It has a momentum,
Okay.
and so it doesn't get stuck.
Okay.
So it kind of like, if it was going really fast at the beginning, then it's going to keep on going, and it just works. You know? What makes it the best is that it works.
Right.
And then you can have a decay rate for the learning rate. So you can start for like some value of the learning rate, and then you can just pass it a parameter that makes it decay naturally. So it's gonna just like find the best place to be, and then it's slowly gonna settle down. It's beautiful.
Cool. Thank you.
Is there another question? We're good to go? Okay, I'm gonna go back to where I was. Okay, so now we have like, so this is really often it's called a multi-layer perceptron, because now I wrote down like a 2-layer network, but I could have a 3-layer network, and I could have a 4-layer network, I can have a 100-layer network, I can have how many layers I want. And so the neurons, sometimes they're called perceptrons. So MLP is for multi-layer perceptron. Okay, let's go back to where we were. Activation functions, summary. Okay, so now you know everything you need to know to train neural networks. So that's an example of an implementation. I'm going to put the slides online, so you're going to have. But this is very simple. You can just ask ChatGPT to code you up like or Gemini to give you like a simple example of an MLP, and it's going to give it to you. So basically, the way that you do it in Torch. So there's 2 main libraries, for machine learning. There's PyTorch and TensorFlow. So in my group, we all mostly use PyTorch. There's JAX as well, but JAX is really good when it works, but it never works. So, but I mean, sometimes it works, so that's what makes it great. But it's a lot of effort. So you should just use PyTorch or TensorFlow. So this is written in PyTorch, and so it has a lot of pre-coded like network layers and functions that make it like very good. So the way that you code up a neural network, so you'd make a class, that's going to be your neural network. And then when you define your class, you're going to define all your layers. So it's going to have a linear layer, it's going to have a ReLU activation in another linear layer, and it tells you like, it just says like what are the hidden sizes. So it tells you like, you give it what's the size of the hidden layer, and then it just figures out what's the size of the matrix it needs to have. And then your forward pass tells you like how to pipe these up together in a way that it multiplies them, and then it gives you the output you want. So then when you want to train it, you define some training set. So you're going to have your X training set and your Y training set. So these are going to be your labels that correspond to the X. You're going to instantiate your model, and then you're going to have some loss functions, and this is cross entropy. And because we're using PyTorch, we don't need to code it up ourselves. It's already there. We define some add-up optimizer, and then we just make a forward pass, calculate the loss, and then backpropagate the loss to apply the gradients to the weights, and then we keep on going like that in a training loop. So that's how it goes. So this is the training loop here. Here, like this. Here, this is the training loop. Okay. All right. So there's a really cool visualization tool for like MLPs. So it shows you basically what are the weights learning inside the neural network and how it's like learning classified between different cities. So you can add different different hidden layers to show how much more complex your decision boundary can get as you add the number of layers. So it's good to get intuition for what's going on. That's the QR code to go there. All right. Questions about fully connected neural networks? Yes.
So like, how do we choose the number of layers, number of like hidden neurons in each layer?
These are hyperparameters. So these are things that you just have to try. So typically the way you'd go about this is you take like a small amount of training data that you have, and you're going to try to overfit to that, just to make sure that you can perfectly learn, like you have enough expressivity to learn it exactly. And then you're going to make it more complex, and so it's going to get a bit worse. And so it's a balance between like making data work more complex versus, and so overfitting versus generalizability. So it's kind of a balance between the two. So typically, I'm going to get to that, but like when you have your whole like labeled data set, you're going to get some amount of it that's going to be your training data. And then you're going to get another like separate set that's like, you just chop it up in 3. So first set is training set, that's the biggest. Then you have your validation set. So you just make choices, you train on the training set, and then you check how well it's doing on the validation set. And then you're going to pick those parameters that make it do well on the validation set. And then at the very end, once you're happy with everything and you're ready to write your paper, you get to the third set, that's the test set, and then you check how well it's doing on completely new data that you've never touched before. And then you get a good idea for how well you would be generalizing to new data that you haven't seen before. So that's kind of like best practices. But choosing the network architecture is kind of the art in this. Other questions? Yes.
Yeah, is stochastic optimization limited to supervised learning or other things as well?
Well, you need something to optimize, right?
Yeah.
But you can so you in semi-supervised learning, you can define the loss that you can optimize. Like anytime that so there's a lot of different kinds of learning that I don't have time to get into, but if you can define a level of unhappiness with the current performance of your network, that's your loss. And then you can take gradients with respect to that. You can train with respect to that. So there's ways that you can train networks without knowing what the real answer is, just by trying to learn structure in your data set.
Okay. Thank you.
All right. So next step is convolutional neural networks. So now that's what we have. So we have some input. Here, we have some hidden layer, and we have some output that are like the 10 neurons that tell us like what are the different classes for our C4 data set. And you can see that everything is connected to everything. So every line here is an independent weight that I need to learn a value for. So that's a lot of weights, and that's a very small network. So you can imagine that this is going to explode extremely quickly in terms of the number of parameters I need to learn during training, right? And so there's another problem with this, is the fact that like if I'm using an image, so my input is an image, and I'm not using the fact that the pixels that are next to each other in the image, they should have some shared information. Now I'm treating every pixel completely independently. It doesn't matter where every other pixel is like physically located in the image. And so what convolutional neurons or neural networks are, they're a way of doing sharing across the different weights and limiting what's connected to some input neurons here based on how physically closely related they are. So basically what we do is we take our input. So this is our input image here. So it's 32 pixels by 32 pixels, and there's 3 channels here because it's an RGB image, but it could be 7, it could be however many filters you have, how many channels you have. And then you're gonna define a filter that's much smaller. And then instead of like fully connecting all of those pixels to the next hidden layer, you're gonna say, I'm gonna convolve this small filter across my image. And now I introduce 2 things. So the first thing is that I'm keeping track of which pixels are close to what in a 2D sense in my image. And then the second thing is that this filter has fixed weights in it. So these are gonna be the same weights that are gonna be sliding across the whole image. So there's gonna be some weight sharing that's going to be happening. So instead of having like a lot of independent pixels, because I cannot multiply in my head, I'm going to have just like 5 by 5 by 3 independent weights that I'm going to be trying to learn. So basically, at one step of the convolution, I'm going to put my filter on top of my image. I'm going to multiply everything in like sum, and that's going to be one value that's going to go in my next like hidden layer. And then once I have that value, I'm going to move my filter and then get my second value. So basically, this is what's going on. So like the orange thing here is my filter. It gets multiplied by the green. The green means my input image. And then at the end of the day, I get like the feature map that's called. That's going to be the pink thing. So visually, like typically, astronomy people have an easy time with that because we do a lot of convolutions when we're processing images with PSF and stuff like that. So that's basically what's going on. So this is another example of like a convolution operation. So I have my filter that's being like convolved across my image, and you can see that the feature map now is smaller than the input map because my filter cannot go like past it. So one way that we can not have that is by padding our input image with whatever value we want. So we can have like 0 padding or something. We can pad it in a way that the output image is going to be the same size as the input image. So that's what's going on here. So now the output like feature map is going to have the same size as the input map here. And by how much we need to pad has to do with what's the size of the filter that we're convolving with. So there's a lot of different ways. And then every time that we have a filter, we're going to get a different feature map. So if we want to have multiple channels at intermediate steps in our neural network, we can have multiple different filters with different value. Like we have a filter that looks for a diagonal line in this direction. We could have a filter that looks for a diagonal line in that direction. And every one of those are going to be like convolved one after the other, and they're going to give different feature maps. So they're going to go in the different channel dimension, and then they're going to be input for the next step of convolution, basically, that I'm going to have. There's a lot of, like, if I look at what convolution layer looks like in PyTorch, it has a lot of different inputs. So when it says, like, valid padding, that's the same thing as having padding is equal to 0. So that's going to be like no padding. So the size of the output image is going to be smaller than the size of the input image. If the padding is 1, there's going to be a 1 like across, and for this size of filter, it's going to do the same thing as having padding same. So same is going to just pad enough so that the output feature mass is the same as the size of the input image that I had. We can also convolve with like stride. So this is not, yeah, so if I convolve with stride 2, what it does is that instead of moving the filter by 1 pixel every time, it's going to move it by 2 every time. So the output is going to be smaller than the input image that I had. Another thing that can happen is that I can have a bigger kernel size, so that's going to also change the output if I don't pad by as much. So if I want to have, and then if I pad by more pixels, then I'm going to have a bigger output than my input. Another thing that we can do is we can do dilation. So the way that this works now is the filter, instead of being like all close together, it can be like, you know, split out across multiple pixels, not adjacent pixels, and that's going to make the output feature map smaller. And another thing that we can do is we can do 1-by-1 convolutions, because 1-by-1 convolutions, they're basically going to be taking linear combinations of all the channels that I have, and that sometimes that can really help mixing the information well for what's going on. Okay, so these are different types of convolutions that we can have. So the way that like a neural network, a convolutional neural network is typically going to look like is we're going to have my input. I'm going to do some convolutional layer with a bunch of filters. I'm going to have here, I have like 8 feature maps. Then we downsample by making it smaller. And then we're going to have another convolution, and then we downsample, other convolution, then downsample. So that's kind of a series of like convolution, downsample, convolution, downsample. And what happens, and then so there's 2 different ways, main ways of downsampling. The first one is to convolve with a stride that's larger than 1. So that's the example that I gave before. And then the other way is to do pooling. So pooling is basically to bring like the pixels together. So max pooling is I take, say, I have a 2x2 filter with my max pooling, and I'm going to take the max of all the 4. And that's what I'm going to pass to the next thing. So if I detect a feature, it doesn't keep track of where the feature comes from. It just says, I have found that feature in this corner here. And here it says, OK, I have found this feature in the yellow, like that. So that's going to make the feature map smaller like that. So there's multiple different kinds of pooling. The most common ones are max pooling by just picking the max in the input. And then average pooling is just taking the average in the input. So these are different things that are already coded up. So that's a complete neural network. So typically what we would have is we'd have like our input image. So that's like a handwritten number 2. It's going to have a convolutional filter, bunch of convolutional filters that give me a bunch of different like feature activation maps, feature maps, sorry. And then I'm going to have pooling to downsample. Then I'm going to have another bunch of convolutions to get even more channels, even more like activation maps. And then I'm going to have another downsampling. And then at some point, I'm going to be happy with the size that I have. So I'm going to flatten all of that into a bunch of vector. And I'm going to put a bunch of fully connected layers that are exactly the layers that I had before, that I showed like in the first part of the talk. And so those bunch of like fully connected layers at the end, they're going to map to my outputs that I want. And typically, most of the weights in a neural network are here because it's so expensive in terms of weight. Like most of the expressivity, most of the magic happens in the convolution, but then most of the weights are actually here. So you have to be very careful not to like flatten and then fully connect too soon, because it's going to be so many weights to learn and it's not going to really be learning anything. It's much better to go deeper, extract more information with like convolutional filters, and have much fewer fully connected layers. Even some networks don't even have any neural connected layers now nowadays. OK, so that's kind of a typical architecture for a CNN. OK. So basically, the advantage of a CNN is like because the filters are like local, that reduces the overall number of weights that we have to learn, which makes learning easier. And it requires less memory on our GPUs. And then, yeah, and then doing the convolution, like sliding the same filter across the image, is going to allow us to learn translation invariance across the image. Because if I'm looking for a diagonal line, doesn't matter if it's like in the top corner or in the bottom corner. If I'm looking for like the image of a face of a cat, I'm convolving across, right? So it doesn't matter where the face of the cat is across the whole image. I'm going to find where it is because it's translation invariance. Good thing, because most images have that property. OK, so that's an example of an implementation. So it's very similar to the one we had before. So we we make a class that's going to have our neural network in it. So we define all of the different layers that we're going to have. So we have convolution, pooling, convolution, and then flattened, fully connected, and then some dropout to regularize, and then another, I'm going to talk later about what that is, and then another fully connected layer. And then the forward pass basically connects all of that together. So first do the first layer, and then pass that to the second, take the output, pass it to the next one, take the output again, all the way to the end, and then you return X, which is like the output of the network. So basically, you define all the layers you want to have, and then you have a method that's the forward pass that just pipes it up together. And that's your neural network. And then, yeah, all right. So very quickly, we have, OK, so now that allows us to do regression for like a handful of numbers. And that also allows us to do classification for a handful of class. But sometimes, like, we don't want to predict like the mass of a galaxy, we want to predict like a segmentation map of where the galaxy is. For example, let's say like one of my problems could be like, oh, I'm like an X-ray astronomer, or like I want to look for bubbles from like around AGNs. And so I want to find where the bubbles are. So I need an activation map that's going to tell me where is like the bubble in my image. So I want my output to be exactly the same size as my output. I just want it to be like turned on at 1 where the bubble is. And that's going to be exactly the map of where the bubbles are, for example, is a thing that I could care about. So I want my input to be exactly the same size as my output. Like in this case, like there's Einstein and there's the segmentation map of where he is in the image, for example. So we know how to downsample, like we know how to do that, but the thing we don't know how to do is how to upsample back to get back like a big image that's the same size as what we had to begin with. So there's a couple of different tricks that we can do to that. The two most common ones are to use transpose convolutions and to do interpolation and then convolution on top of the interpolated layer. So transpose convolutions are basically to pad your input with like a bunch of stuff, typically zeros, and then to do a convolutional filter on top of that padded image. So you could just pad like this, like by splitting your pixels across your image and then get a much bigger activation map, or you could just pad like all the way around, not in the middle of your pixels, and get a bigger activation map. So these are two possible ways to do transpose convolutions. And then the other way of upsampling is resize convolution. So then you'd just basically be interpolating on a bigger grid whatever feature map you had. So you could do nearest neighbor interpolation, or you could just do linear interpolation, whatever type of interpolation you like. And then on top of this map, now you do a convolution, and then the activation map is what you pass to the next layer. So typically, the first way of upsampling is going to give you this kind of checkerboard pattern on your images that you're going to generate that are not really physical or desirable and very difficult to get rid of, whereas the second way of upsampling is going to give you much smoother maps. So typically, it works better to do that. But it could be that you have a problem where the first kind works better. OK, so the default architecture for image-to-image mapping is something called the U-net. It's called the U-net because it's in the shape of a U, like that. So basically, it takes the input image, it downsamples, convolve, downsample, convolve, downsample, convolve, downsample. That's the bottleneck. And then upsamples, convolve, upsample, like that, all the way to the top, where you end up at the same size that you started with. But then on top of that, you also pass whatever you had before downsampling here, and you concatenate it at the same layer than what you had. And you do the same thing at every level of your unit. And what ends up happening is that it's basically learning every different scale what is the information that's important. Because here, your feature maps are sensitive to like, your filters are looking for very small scale features. And then when you downsample and you have a filter that's the same size, it's actually looking at much larger scale features in your input image because you've downsampled. So it's looking at like larger scale information and then even larger scale information and then even eventually like all image information, and then you just sum up all the information that you factored out in terms of like scale. So it's kind of a way of looking like scale by scale, decomposing the information that you have. And so that's what makes it a very powerful architecture. So that's kind of like the default architecture for image-to-image mapping. And then I have a whole bag of tricks for things to do, but I don't know how much time I have. So maybe you guys are bored with practical tricks and you'd like to do something else. I don't know. But yeah, I'm going to give you like this is like what we talked about, training set, validation set, test set, loss function for the two different like diagnoses you can have with your loss function, overfitting versus underfitting, early stopping, decaying your weights to regularize, dropout, and data augmentation with symmetries of your training set. Yeah, pre-processing the data is important. So yeah, I can go through that if you want, but you can just read it in the comfort of your home if you want. I don't know. How much time do I have left? Because I can just start talking about fun stuff now. Because I started at 5:05, less than half an hour ago. Okay. All right. Maybe we can just take questions. Do you guys have questions?
So for the parameter matrix W, how dependent is all of this on the input values that it first has, the initial values?
Oh,
that it
that's
has?
very, that's a very good point. That's like the next slide, I think. Oh, no, that's, so yeah, that. So there's a lot of ways to initialize your weights, and figuring out what's the right way to do it so that it doesn't explode is very difficult. But it's not very difficult, but there's some thinking that needed to happen. So you could think, okay, like I'm just going to start with random number, and then it just like kind of like it just collapses in a really bad way. If you say, okay, I'm going to start with zeros, then it's just doesn't learn anything. I'm going to start with ones, it's going to be like very bad too. So you actually have to do the kind of a fine balance between the two, because you have to balance your activation functions versus like how the weights at every layers are doing, so that you can still have gradients. Because if you like remember, like say for example the sigmoid function or like the tanh function or the ReLU, there's places where there's no gradient. So if you end up like with really large value, like for ReLU, if you end up with negative values, there's no gradient. So all the neurons that land in the zero land of the ReLU, they are dead forever because they don't have gradient. They output zero and they don't move because there's no gradient.
I see.
Right? So you have to be careful with that. Same thing with like a sigmoid function, like it's very flat in the large positive and negative values. So if you end up there, like it's going to be very hard to walk back because the gradient is so small. So initializing the weight in a way that you get a very nice like Gaussian, so not Gaussian, but like kind of like standard deviation one, like mean zero value at every layer is tricky. It's called Xavier initialization, and that's the way we do it. And it's coded already, so you don't have to know, but that's what it is.
Okay, that's cool. The one other part is for the padding, did you say we should, it's better to use just zeros or random numbers?
For the padding, it depends what you're doing, right? Like if you're a cosmologist and you have like a cube and you're trying to build an emulator, I would say just do periodic padding because that's how your box is anyway, right? Because it's a cosmological simulation. But like it depends. If you have like if you're doing convolution on a sphere, like you should probably do periodic things because the sphere has that property. If like there's no information on the boundary, probably just use zeros because it makes sense. If you're thinking about using a log after, don't do zero because that's not going to go down well. So it's very problem dependent. Like it's doing machine learning doesn't allow you to not understand your data. So you still need to understand what your problem is, and you still understand your own data to know what's going to kind of do well. But yes, zero padding typically works well.
Okay, thank you very much. That was very helpful.
Okay, there's one thing I didn't quite understand is when do we use pooling? Because you talked about convolution, upsampling, downsampling, but when is pooling?
So pooling is a way to downsample.
Oh, okay, so it's a way to downsample.
So yeah, so I know I went through it really fast. I kind of like zoomed through a whole undergrad lecture on machine learning. So because when you pool, what's going to happen is that like you start with say a 4x4 activation map, and then after pooling, it's going to be like 2x2 if you do 2x2 pooling.
Okay,
so it's going to make your map smaller. So then if you like have a convolution on top of a map like this, it's called the receptive field, like the place where you're going to be sensitive and your input image is going to become much larger. So it's basically effectively going to be looking at features that are over much larger scales.
Okay, so it's the same thing as the padding, right? It's a zero padding. Is that right?
No, it's not zero padding because the max pooling is basically going to look at where you found some feature and say, okay, I found it and it was in that corner, but it's going to lose resolution in terms of where the information came from. So like
Okay.
personally, I tend to like strided convolutions better because they don't lose the information of where a feature was found. It gets encoded in correlations between pixels. So it does the same job of downsampling, but then you lose less information. And I
Okay.
find that for physical problems, usually that makes kind of a difference. Like when you're trying to really squeeze like as much performance as you can get some extra performance by looking at strided convolution.
Okay, good. Thank you.
Just to check, Laurence, are you going to post your slides on Slack? Are you okay with that?
Yep.
That would be very helpful, yes.
Yep.
because-
Yeah, I put a lot of stuff, more than I have time to say in the
Yeah,
slides.
no, some good.
There's already a couple of people posted pointers to visualizations and similar things on the Slack channel. So it's going to be great to continue discussion there. But you can even continue for a bit or you can stop here. It's up to you.
I'm going to give you a teaser for tomorrow. Is that okay?
I'm sorry.
I'm going to give you a teaser for tomorrow. Can I do that? Like just a like intro to the next things we're going to do?
I didn't understand. You want to leave for tomorrow? Whatever is fine. You decide.
Okay, tell me how long you want me to talk for.
How about 10 more minutes now and then we stop? How's that?
Right? Yes. If you guys are tired, it's fine. Like I understand you had a full day. Like raise your hand if you want more. People do not want more. People are so done. No, I'm gonna keep on going tomorrow. I'm gonna let you guys rest.
Dragon, do we have any dinner suggestions since or no? So what do we do for dinner?